We're going to look at solving exponential and logarithmic equations today. This section really ties together, this is focused on section 4.4, which really ties together everything we've done to date with exponential and exponents and logarithms. I pulled several examples from the textbook, so if you want to go back and reference these later, this will be easy to do it. First is a basic example. Problem number 24 says 10 to the x power equals 8.07. Well, the key here is identifying where your variable is, which is the exponent. So this is automatically an exponential equation. What I need to do is to solve for that exponent, and you should know by now one of the things I try to reiterate is that logs give you exponents. So we should be able to quickly transform this entire problem from 10x equals 8.07 to x equals log of 8.07. Notice I didn't put a base down there because I'm using 10, so it's understood to be 10 when there's nothing written. And when I solve this with my calculator, log of 8.07, I simply get x is 0.907. Let's look at a similar problem, number 30. It's similar, yet a little bit more complicated. This is 9 e to the x equals 107. Notice how the 9 is a coefficient. It's in front of the e to the x. So the first thing I want to do when I solve this is get rid of the 9, bring it to the other side. Now I get e to the x equals 107 over 9. Now we can do this one of two ways. We can convert it, or we can use our natural log on both sides. I'm going to use the natural on both sides instead of converting like I did in the first example, just so you can follow along and see exactly what the book's doing. One of the ways to get rid of e's is to hit both sides with a natural log. We've studied the properties last week, where the natural log of e to the x is just x. They're inverse functions, so they cancel each other out. And you wind up with x equals natural log of 107 over 9. And when you plug that into your calculator, you get x is 2.476. Moving right along to our next example, this one's a little bit different because we get 7 to the 2x plus 1 power equals 3 to the x plus 2. The reason this one's so different is we have two completely different bases. But again, our variables are in our exponents. So what we're going to do is hit both sides with our natural log. We get natural log of 7 to the 2x plus 1 power equals the natural log of 3 to the x plus 2 power. The reason we want to hit it with the natural log the right way is twofold. Number one, we want to solve for the exponent, so natural logs or logs and natural logs give us exponents. But second off is that logs give us this wonderful property that if I have an exponent inside my log, I can bring it out front. So this 7 to the 2x plus 1, once I hit it with the natural log, I can bring the natural log out, the exponent out front of the natural log. So natural log of 7 to the 2x plus 1 is the same as 2x plus 1 times natural log of 7. I do that same thing with the other side, x plus 2 times natural log of 3. Now I'm going to distribute each one of these natural logs into each one of these terms. So this is 2x times natural log of 7 and 1 times natural log of 7, which is just natural log of 7. This is x times natural log of 3 and 2 times natural log of 3. Now I have a very linear equation. These natural logs look ugly, but they're just constants. So treat them as such. I have two variable terms, one on this side and one on this side. So I'm going to bring them to the left-hand side. I'm going to get 2x natural log of 7 minus x natural log of 3 equals 2 natural log of 3 minus natural log of 7. Now what I'm going to do is, I didn't show it in the step, I factor out an x from these two terms. So I pull out an x, and I'm left with 2 natural log of 7 minus natural log of 3. So I'm going to divide that by both sides. So I get x equals 2 natural log of 3 minus natural log of 7 over 2 natural log of 7 minus natural log of 3. Now the hardest part is probably should be plugging this into your calculator because this is going to get kind of ugly. Remember to get your parentheses around your entire numerator before you divide, and then put parentheses around your entire denominator. But you should wind up, once you round up, keeping things consistent with 3 decimal places, you should get x equals 0.090. Now this next one is very interesting. It's very interesting because we go from having just 2 terms in our exponential equation to 3 terms. I have e to the 2x minus 2e to the x minus 3 is 0. Now, I'm going to do this a bit different than I've done before. Usually I bring all my variable terms on one side and then hit it with a natural log. Your natural logs don't distribute over plus and minus signs. So I'm going to use a technique here called substitution. This is a square term up here, this e to the 2x, that's squared. The e to the x is my first degree power, if I want to think about that, minus 3 is my constant term. I'm going to let u equal e to the x. That makes this first term e to the 2x. This simply becomes u squared. This e to the x becomes u, so I wind up with u squared minus 2u minus 3. I now have a very simple polynomial, in fact it's a trinomial, that I can factor. This factors to x minus 3 times x plus 1. And if I solve each one of these, I get u equals 3 and u equals negative 1. Well, we need to take a step back and remember we substituted. I'm not solving for u, I'm solving for x. So I need to re-plug back in e to the x equals 3 and e to the x equals negative 1. Now if I solve each one of these, I get x equals natural log of 3 and x equals natural log of 1. We can automatically eliminate this because we assume when we're dealing with logs that we have a positive number inside the log. A non-negative number is what I should say. So I can cross that one out. My only answer is natural log of 3. Let's move into a couple examples for logarithms. This first one's a basic one. Log base 2 of 4x plus 1 equals 5. Remember, logs give you exponents. So my exponent is 5, my base is 2, so I'm going to rewrite this as 4x plus 1 equals 2 to the 5th. 2 to the 5th is simply 32, so I get a very simple equation. 4x plus 1 is 32. 4x equals 31 when I subtract 1 from each side, and x is 31 over 4. My next example, let me get it onto the screen for you. Here we go. Log base 6 of x plus 5 plus log base 6 of x equals 2. This is a really nice problem in the fact that with dealing with logarithms, I can combine multiple logs into single logs as long as they have the same base. Notice it's base 6 here and base 6 there. So when I'm adding logs, that's the same as making a single log and multiplying the stuff that's inside. So what I did is I made this log base 6 of x plus 5 times x, which was x squared plus 5x. Now this becomes a lot like what we just did. I now have a single log equals a constant. I'm going to rewrite this. Logs give you exponents. My base is 6, so that's 6 squared, and the other side is simply what's inside the log, x squared plus 5x. If I reduce the 6 squared, I get x squared plus 5x is 36. Bring the 36 to the other side, and I factor. I get x plus 9 times x minus 5 is 0. That gives me negative 9 and positive 5. But I have to take a step backwards because I plug in a negative 9 into here. I get negative numbers in my original equation for my logs, and I can't have that. So I eliminate the negative 9, and I have a single solution, x equals 5. Hope this helps you this week. Good luck.